Okay, so welcome everyone. Thanks all for joining. So this is our first discussion about the impact of AI and medical imaging in the times of COVID-19 pandemic. So, we've launched this Arterys Marketplace Community. Okay, people are joining and I have to admit them, sorry. So we started this community a bit more than a month ago, and we are very excited to see how big and rich it has grown. And we are very proud to bring all of you brilliant people together and support your incredible work to improve care, mostly. So as you know, some of the scientists and engineers here in our community have been trying to develop AI models on chest X-ray and chest CT specifically to detect or diagnose or track COVID on medical images. And today's topic is actually based on some requests from you guys who are looking to understand the data set better and interact with clinicians to learn more about the feature that you're looking at when you're training your AI models or when you're testing them and validating them. And this is why, so today we have a group, I'm looking at all of you. So we have a lot of you AI developers and engineers, but we also have Dr. Albert Hsiao here, who's a cardiothoracic radiologist and the head of the IDA lab at UCSD, who can help us address some of the clinical questions around the data and the labeling of the data and training a model, because he has extensive knowledge in that domain. We also have, as I see, so we have Uli and Joe, which are our internal ML team at Arterys, that could also help you share their expertise with building AI models specifically for lung CT. And we also have Eric, I don't know if we have Iva as well, that are more on the annotation side of things and work with annotators and clinicians on and creating labeled data sets. We have Rohan and Rahul, I guess, and Darshan. I'm looking who else is here, and Odas and Arsen, who actually are the ones that are using those labeled data sets to build their model and train them. So I wanna start this conversation by asking you, some of you AI and model developers, what is the challenge today when you're trying to build your COVID-19 models? Who wants to go? Maybe Rohan, you want to tell us a bit about your how you're training your models and what is the challenge that you're facing?
In terms of challenges, in terms of like training our model, I would say that one of the challenges we had was overfitting, and that was kind of an issue that we solved by implementing early stopping. But other than that, we haven't really had any notable challenges that we weren't able to overcome.
So the challenge you said is overfitting. Is that due to your limited access to the data set? How are you, where do you find the data set today to train your model?
Oh, we actually made a little mini presentation that kind of explains some stuff about our project. Would you mind if we presented that really quick?
Yeah, for sure. Go ahead.
Okay. Rahul, are you there?
Yeah.
Okay.
Are you sharing your screen, Rahul? Sorry, Rahul, are you going to present? Do you need to share your screen first?
One second.
Okay.
Okay. Okay, can you guys see it now?
Yeah.
Okay.
Cool.
So our model, we decided to name it just CoronaNET for now. Pretty simple. And I'm Rahul Kumar, and
I'm Rohan Bhansali.
Yeah. So the dataset that we used was from UCSD. There's 300. When we used it, there were 349 COVID CT images and 397 non-COVID CT images. So pretty simple.
And then with those images, they were all of variable size and ratio, obviously. So we performed by cubic interpolation to downscale them all to uniform size of 500.
Sorry, Rohan, sorry to interrupt, but I don't think we hear you clearly. Can you speak closer to your microphone?
Yes. So yeah, as I said, the images were all of variable shape and ratio. So we performed by cubic interpolation on all the images to downscale them to uniform size of 512 by 500.
Once we used bicubic interpolation, we applied the Laplace operator as a pre-processing filter. And the reason we did this was to make some of the features more apparent and highlight some of the edges in our images. And we also applied affine transformations to basically rotate the images and make our data set larger, because the original data set didn't have enough images to train a model properly.
Now onto our model itself, CoronaNET.
Sorry about that. Oh my god. Okay.
Okay, so this is like a little overview of our model itself. So I was just going through the 7-layer convolutional neural network. We utilized the binary cross-link function and trained it with a batch size of 5 over 50 epochs, which equated to a runtime of about 700 seconds per epoch. This resulted in a 92.2% validation accuracy and an F1 score of 0.8975. So yeah, and then you can basically see the progression of our model over its epochs. As you can see at the end, there was a bit of overfitting. That's what I was talking about, but we basically reverted back to what was around like the 46th or 47th epoch, because that's when it reached its optimal performance.
And then for our future work, we're looking to continue optimize our model, and then we're going to work on finding more justification for exactly why the Laplace operator had an effect on our data set and why we use the affine transformations. And then we're going to try to get our model on the Arterys Marketplace and also get a paper peer-reviewed and published. And that's basically it.
Pretty cool work. I just have one question, just out of curiosity. How did you arrive at the architecture that you proposed? Did you like run hyperparameter search or try out other things?
Yeah, so we actually did try a couple other architectures, but I think the main thing was that they weren't necessarily additionally accurate, but they had a much longer runtime, so it was much more computationally expensive. So that's why we chose to use this one. It's a little bit more simple, but it equated to basically the same accuracy.
Oh, that's pretty cool. Yeah, that's super nice if the simpler version reached the same accuracy.
Yeah, exactly.
So I had a question. You said your data came from UCSD. Is that an open source database?
Yeah, it's an open source database available on their GitHub. And I actually believe Arterys, the spreadsheet I was looking at earlier, it's also listed on there as well.
Okay, so it's an open source database of CTs. Okay.
Mhm.
And did you need any annotation, or how would you improve your model today? Like what are the next steps for your model? Do you intend to improve it in some way?
Yeah, so we were looking at a couple things, including perhaps maybe a little deeper model. Because as I said before, different like deeper models are not necessarily more accurate, but perhaps like instead of 7 layers, a 9 layer neural network could perhaps be more efficient in recognizing COVID. But as of yet, we don't really have any immediate plans, but we're thinking of going somewhere in that direction.
Sounds great. Is there any questions from the audience here? Maybe Darshan, do you want to share also your experience with working on building COVID models?
Actually, yes. I took a different approach to this. I didn't go with CTs. I instead went with X-rays. So the thing with X-rays is that usually there's more data available with the X-rays, of course. So I actually began with like a normal distribution of COVID versus non-COVID, but turns out that the amount of data that we have currently, it doesn't make sense doing that. So what I did is I changed the problem statement itself. I tried to approach it as more of a pre-test basis. Okay, so if a person with the usual symptoms, he comes to a doctor, then he can get his X-ray done, and then after that the X-rays run through the model. After the X-rays run through the model, the predictions, and based on the predictions, basically you will go for a PCR test, because PCR tests are of course more reliable than X-rays or CTs in general. So what my approach to that was that according to many of the radiologists here, what I did was I looked more at the opacity side of the models. Okay, so my data was based off of multiple data sets like the NIH, RSNA, and various basically random, even I've picked some samples from Google itself. So so what I did was my split was more like 9.5 thousand versus around 15,000 images. So 9.5 for the opacity ones and 15,000 for the non-opacity ones. So after that, I pre-processed it by varying the brightness, varying the different exposures and stuff like that. So basically for avoiding overfitting. So I actually experimented across like different models, different convolutions, different feature extractors, different pre-trained models. Been working for this for almost 2 months. So it turns out that the ResNet 101, it works really well with this opacity detector, as it did for, I think, one of the models that is being deployed, I guess, on your sites. So I went with that, but I felt like every model can do better. So what I did was I made my own custom model, keeping in mind the ResNet and the Inception or Exception models, okay, which is available on my GitHub, I guess. So you can go check it out. The link is on the Slack. Okay, so the main challenges, I basically had only 2 challenges here, is that because of the limited amount of data that we have, the model usually looks at something other than the lungs, like maybe some text or maybe some other bone overall, like a different bone that you don't know, that you don't want it to look at. Okay, that was the first problem. The second problem was that specifying, without any annotations, without any bounding boxes, nothing, I wanted to look at opacities. So, and of course, because the data distribution is such, you can't, there's not enough data. So basically you need more than for building our own custom models, you need around like at least 50,000 images of both included. That's fine. So that is what the issue was, that the data is very limited and without annotations. So I came up with this architecture thinking that the way it's spread, is that first there are at least 1, 2, 3, 4, 5, 6. So there are 6 layers of feature extractors only. Okay, so with that in those 6 layers, each layer has a separate layer of usually 2 nodes. Okay, so every node has different amount of parameters, filters, kernels, different stuff. Okay, so you can look up the architecture. So they're on my GitHub. So during the training itself, as the previous presenters, I think Rohan mentioned, that overfitting is a major problem here. So I too used early stopping like they did, and it turns out that it's quite effective. So I actually noticed that the lesser you train these models for, it's more harmful for the model itself because it doesn't generalize. So I first then like I experimented. I used the Keras tuner. I ran it through. I ran it for approx like 2 days. It was just running, okay, for the hyperparameter search. So after that, I came up to a conclusion that these are the best hyperparameters. Ran the model again, but it does overfit after like the I guess the 14th or 15th epoch. Okay, so at that point, if you early stop, it's still fine. Like I get an accuracy of around I guess 90, 92, 93, around 93 validation accuracy. And then a test accuracy separately, as mentioned in my GitHub, is 95.61%. Okay, so that is an accuracy for opacity detection, and it's not necessary. Like if you show it a pneumonia sample, it will still classify it as a positive, but that doesn't mean the person has COVID. Okay, so
Right.
this just acts like a pre-testing base, because of course, as mentioned in the group itself, the Slack group, that X-rays or CT scans aren't completely trustworthy for analysis and diagnosis. So I took this separate approach, and I've gotten amazing results from it. And by the heat maps and the gradient visualizations, I can see that it's focusing on the opacities perfectly. And the initial problem with the models was that I was having a lot of false positive cases, like the negative samples were getting classified as positive. Okay, that is because of the data distribution. You can't help it a lot. So with this model, I've tried to minimize that, and I've minimized it to a very decent level. Like I think I extracted a 3000 image test data set of just normal X-rays and ran it through the model. Only got like 41 or something wrong.
Okay.
So that's like a 98% accuracy on an unseen set of just normal X-rays. Okay, so that was the entire workflow of mine. And then, eventually I'm planning to maybe once when we get more data or something, then I'll maybe retrain the model, look how it goes from there.
Yeah, thanks for sharing that, Darshan. So your model is today, I think you've also worked on with the SDK, so it's ready for integration to the Arterys Marketplace, and we're very excited to put it into the hand of clinicians soon. I'm wondering, so you'd mentioned two challenges here and I feel like we have some people on this call who could help with addressing those. I don't know if you have any thoughts on this, but it sounds like the limited amount of data and the annotations are the main two things lacking. Albert, what do you think about that? How can we address that today?
Yeah, I mean, I think there are some initiatives that are ongoing, like at the RSNA and ACR, that are trying to aggregate some of these data sets together. It's unclear what they will release, whether it'll just be images or what degree of annotation they will include in that. I imagine they won't include a huge amount of effort in annotation, because that does take some time to do. But at least they'll produce something. But I also don't know what timeline. But what I have heard is that for those initiatives, they do have buy-in from a lot of institutions across the country. So I believe they will get a fair number of images. But they won't be 300. It'll be more like thousands, I imagine. At least I would hope so.
The current data set for the one that is hosted on the GitHub, it's got its own annotations now. So it's still limited, but it's got around 170 images with annotations now. So if anybody wants, for X-rays and CTs both, I guess. So if anybody wants, I'll link to it. If you just get back to me with that. The main IEEE 8023, the user's data set, you can go check it out.
How did you get these additional annotations?
The additional annotations, I'm not really sure, because the owner of the GitHub repo got them from I'm sure it's some trustworthy source. I'll link to it in a minute.
Okay. Thanks.
I have few questions to Albert.
Yeah,
Yes.
sure.
Okay, first of all, I'm Sam. So okay, when I made the feasibility study for COVID-19 detection, okay, so one of the things which everyone are saying is that the clinical process versus the AI process, the usability, like, wait, I'll just share a screen.
I didn't understand your question. So, sorry.
Yeah, one second. I'll just share my screen. Okay. Okay, fine. I'm just seeing how to do it. Okay, fine. So my question is like, there has been concerns regarding the healthcare workflow versus the AI model workflow. So like, how do you see the feasibility of this? Like, the common concern is that we have to disinfect the place which takes the CT scan or X-ray. And yeah, one more question is like whether we have to choose the CT scan or just X-ray, and what are the differences between them, and like which gives us a good amount of data. So like, I have these two questions. So can I just answer them?
Yeah, I mean, I think I understand what you're asking. I mean, well, maybe I'll start from a clinical perspective. The way that we use X-ray is it's a very inexpensive and relatively cheap modality and that's widely available everywhere in the world, right? So CT scanners are considerably more expensive, and they're a lot more involved to scan than an X-ray. So that's some basic principles. We use X-ray for a lot of different things. Given that it's a lot cheaper, we can do serial X-rays more inexpensively. So meaning you can do one every day or multiple in a day if there's a change in the status of a patient. And so those are things that we do routinely in practice here in the U.S. and certainly everywhere in the world has slightly different ways that they use X-ray and CT and slightly different availability of those two things. CT scanners are not the most expensive things, and there are older scanners that are now, like, they after they're they may be commissioned in many parts of the world. Older scanners maybe even are just as good for something like COVID infection. So in China, I think in the early experience, they ended up scanning a lot of their patients with CT, and it's not a bad idea, but it's just not something that we do in the U.S. So keeping those concepts in mind, I think you get the picture that you may need to have algorithms for each modality, and their use cases may be different depending from country to country. So hopefully that's helpful. We like I said, we don't do multiple CTs in a day for a patient, but we do that for X-ray, and hopefully that's helpful. The question about how you integrate AI into the clinical environment is an important one. I think there aren't many institutions that have done that yet. I think with this coronavirus pandemic, it has accelerated some things. We've had AI algorithms on on the back burner in our lab for a long time, and have been waiting for a platform like Arterys to come in and allow us to use them. And so that there, I think that's an important aspect of things, is that it's not used.
That is the key differentiator according to many people, because whomever I spoke to about this, what they say is that will this integrate into our workflow, like we need to upload this to another third-party software. So when it comes to third-party software, there comes the privacy issues. So okay, let's keep the privacy thing aside as of now. So like how do they integrate into a local environment? So these are the questions which are posed to me as a deep learning engineer. So okay, so the CT versus just X-ray. So we can conclude it as like we need to develop a model for both the approaches, right? Can we conclude it that way?
Of course, yes, I think so. And there are many use cases. So diagnosis of COVID, there are papers, of course, that what people write, and they'll say, oh, I can diagnose COVID pneumonia from something else or whatever. Those are not necessarily always the relevant questions that we need to have solved. So it's important to understand how the algorithms will be used, so that you're developing your algorithm with that clinical endpoint in mind. It's not something that you necessarily want to, I mean, it's always fun to analyze data and see, invent a problem to solve. But I think if you want to create a solution, create an algorithm that actually has clinical application, then you really do have to find out what are the, what's the direct application that that people would want to have AI help them solve.
Okay, fine. I will conclude this question as an uncertain. Okay, because even though still now it's under a bit of cloud for me. So my one more question is like, can we have any other approaches other than a classification approach, like COVID, non-COVID, or else just we are just classifying whether the patient has pneumonia or not pneumonia? So I just want to like whether can we include the segmentation annotation in this, or bounding box annotation, so that we can have a more reliable information rather than the probabilities, because deep learning is has always been considered as a black box. And even I've been like researching into many kinds of gradient visualizers, but still I don't trust them, to be frank, because
that touches on a very important point, and why I'm actually not a fan of classification or even bounding boxes. I think they're not adequate for medical imaging. And the main reason there, and that speaks to the whole question of what is the problem that you're trying to solve. I think in other applications of AI, that's okay, that's adequate, because you don't necessarily need to have an expert at all times interfacing with that. So like in a self-driving car, detecting each pedestrian on input images or traffic signs, those are just sort of intermediates that are important, but are not like really diagnostically essential. In imaging, it's not just important to have a classification of whether it's a cat or a dog or a pneumonia or not. The classification is a piece of the question. The other question is, where is the pneumonia, and how certain are we of that diagnosis at that location? So that's actually what drove us to create the probability map strategy, is that that's a little bit more informative, considerably more informative, I hope, to the actual clinical question, which is, did my stethoscope, the loss of breath sounds in the right lower lobe, did that match with what's on the X-ray, right? Like, so you need to have the localization. It's a really important aspect. And then the other aspect is this patient getting worse? Yesterday he was not doing well, but today he's not able to breathe, and we have to give him more oxygen. So is the X-ray getting worse? Is the CT getting worse? Those are the clinical questions, right? So to answer those kinds of questions, the classification is not going to help. Right. So you really need this localization and this time domain aspect of things. So that's what drives us in terms of what data do we need to collect, what algorithms should we develop, and they may not be just sort of the well, you know, ResNet classified this, you know, in a different application, non-medical application. That may not be what we actually care about clinically. So that's what I mean. You know, you have to really wrestle with the clinical use, clinical utility of what you're trying to build, and then target your application specifically for that need.
Okay, fine. So how can we conclude this question? Like, what my question is, any other things other than classification? So that's my question. How can we conclude this?
Yeah, I mean, I think if you, hopefully you've taken a look at the paper that we published. You know, I think it's always good to have the foundations of peer-reviewed literature. So we published 2 papers on just the essentials of this probability map approach. I think if you take a look at that, that may be helpful. There are public data sets that you can reproduce that work on, including the RSNA pneumonia challenge. Just approach it from that standpoint. And then certainly you can also take a look at COVID-specific data as it becomes available and target it for that. I think that's really the best strategy is sort of get that foundation of this other style, this other approach.
Okay, so I have posted a link in our Slack group now. So it's a tweet link done by Joseph Paul Cohen, the famous IEEE 8023 GitHub repo. So in the comment of it, like there is a comment that someone was using pediatric negatives versus adult positives. Okay, so like as a deep learning engineer, we don't know how to differentiate what I can say, a sample, whether it is an adult one or it is a pediatric one. So like there are lots of things which are like behind those images which we are unable to understand. We are just like plucking those data sets and then we are just fitting, and we just think that we are unable to see. So like how we can mitigate this? I think we need to focus more on data, because what I believe in is that according to in deep learning, what you're given is comes out. So garbage in, garbage out, that concept I'm saying. So we need to focus more on data. Like we need some persons who can point to these, because I don't know, all these samples are pediatric negative and adult positive. So this is a big bias in my opinion, because whenever we show a sample of a pediatric negative, even though unfortunately that pediatric sample has COVID-19, it will be diagnosed as non-COVID-19, and it will definitely backfire us when we don't understand the data. So that's why I didn't like focus much on the architectures and then all those kinds of things, because all those are secondary in my opinion. The primary goal for us in our setup is we need to finalize the data. We need to be like specified persons who are responsible for the data, explain more data, so that there should be a better communication between the person who handles the data and then the one who designs the models. Model designing can be done. There are a lot of approaches. There are a lot of even some people specify the overfitting approaches. There are a lot of things which we undergo in our daily life scenarios. We can mitigate that, but the thing which we cannot mitigate is the data set. And yeah, unfortunately, the painful thing which COVID-19 has shown me is that we don't get the data on a novel virus. So that is my question. So what can we do there?
Yeah, that is a good question. So from what you're saying, you understand how important it is to actually work together, like with the clinicians and with experts to actually determine whether the data we're working on is a good data set and is the right thing to train our model on. And I'm hoping also you can find those answers in this community and in this Slack group, because we have different kinds of expertise, and we will try to work together to help you with that. As Albert said, so I think that like the timeline would be probably a bit those data sets are being gathered right now, but we still don't have access to them. But whenever we have access to them, we're making them available for you. I also believe that maybe Joe can speak to that, but later we have also other initiatives to help you guys annotate, or like provide you guidelines for how to annotate data sets, or how to evaluate good labeled data sets. I don't know, Joe, if you wanted to chime in here, or I could just keep going. Okay.
Actually, I have some questions.
Yeah, Darshan.
So you mentioned two important things. One is that you don't have trust in gradient visualizations.
Yes, exactly.
Why is that so, may I ask?
Actually, we can't say that it completely we can say that as two things. Okay, so one, when you do back propagation, all those gradients, it must like satisfy the two things, completeness. So we can say that the completeness thing as like I can say, I'll just share you a paper. Okay, so maybe you can see in that paper. It should be like the gradients which represent all those changes in the image. It should be like we need to see it as a value. That is called completeness testing. I'll share it in my GitHub. I'll share my GitHub repo in Slack. So I have explained about that in some post. So yeah, we need better things other than the highlights on an image, in my opinion. So that is why I say I don't trust, because even when I have worked with the Mura dataset, so the Mura dataset, it is dislocation and then fracture pinpointing dataset. So like even though my model has scored excellently well, which I can say, so but there are some region of interest which came outside of the Xray, or else which came like a bit apart from the region of interest. So that's when I started to think like we need better things other than the gradient visualizers. So like we need the usage of bounding boxes, or else we need localization other than the normal probabilities. So that's my opinion.
Basically, so the back propagation it's just differentiation. So if you have like huge values and stuff, it will get differentiated. It might appear outside of the X-ray, but most of the points, if they are present inside the X-ray and at the point that you're focusing in, I don't see what's wrong with visualizations.
Actually, we can use these kind of visualizations in like non-trivial. For example, if you're one second. So imagine the scenario. We are localizing a vehicle. Okay, so in that we are just using the grad cam kind of thing. So like you can see that the grad cam area can be like a bit larger when compared to vehicle, and it is not going to be what I can say life threatening. But here when we like for example, if a COVID-19 patient has day 1, day 2, day 3, day 4, day 5, and if unfortunately our like a gray the gradient visualizer, it's like changing in shape over these samples. So we can't say that whether the patient is improving or else like or they're improving in a negative way. So these kinds of things are we have to look, because the gradient visualizer is not concise. You and me, we both know, because we have worked a bit on it. So when it comes to clinical works, we need more precision rather than a bunch of pixels. We need more concise. I will share you the paper link. So in the paper link, that author has highlighted a lot about the gradient should be concise when it comes to the region of interest. So yeah, it's better to read that paper.
Yeah.
And it takes a lot of time to understand it.
Yeah.
Thank you, Sam.
So actually, I had another question. So you were talking about the data set bias, and how pediatric X-rays are again classified falsely. Yeah. So I actually came across this problem while building my model. So there's this data set on Kaggle. It's called
pneumonia.
The Paul Muniz X-rays data set. Okay.
Yeah.
So it has got a lot of samples of pediatric X-rays, and I know that it gets biased. But if I see, that's how I tackled it. So if you have enough data, then it will not be a problem, because it wasn't a problem for me. So I collected pneumonia-based data from literally multiple data sets like NIH, RSNA. Then I had some of the ones that you guys are using as well. I also had the ones which were there in the data set on Arterys, the CSV. So I feel that that's just the amount of data that you have of pediatric X-rays, that is the issue here, and not the X-rays itself. So if you have enough of those X-rays and enough of other X-rays like of adults, then I don't think it's an issue here, because it generalized pretty well for me.
Yeah, actually, the problem I highlighted it with an example. Okay, as an example, I said that we don't know to differentiate between a pediatric X-ray and an adult X-ray. So I just highlighted the issue with an example. And yeah, who knows that there can be many more biases within this, because these data are not peer reviewed. And yeah, you can understand what I'm coming to the point. So we need a person who will filters these things.
Yeah, so I'm hearing something in common here, is that in the absence of good and a large amount of data, we're kind of using whatever we have to build something. I don't know if Julie, you wanna. I know that you've done some work on transfer learning. Do you think that is something we can use here on those models that have been trained on a limited number of data?
I think in general, I would say yes, but the thing is with transfer learning, you always restrict yourself to a set architecture. So you would have to basically take an architecture that might be suboptimal for that specific task that you're trying to fine tune on, which is one negative point of it. But the positive thing that we could actually use it for is if anyone wanted to use more complex models that actually have a problem converging on a small data set. If you use larger models that have been pre-trained and then fine-tune them on the limited data set, I feel like that would be super valuable if you use other models. So if you actually find an architecture that is more complex and more fitting to the task, I feel like that'd be great. But then again, just like Rohan and Rahul mentioned earlier, they were trying more complex models, but turns out the super simple model was just achieving the same performance.
Right.
So I feel like maybe transfer learning in this sense would potentially not really improve the performance overall, but maybe the generalizability, which would be super, super good to have. It's just more difficult to test because we can't evaluate. We can't really just evaluate that just with performance metrics. We would need a representative data set that we can actually then generalize on and perform well on.
Yeah. I don't know if there are other people here that have anything to say or have any questions.
Yes, I have one question. This is Jean from Ingidata speaking.
Hi, Jean.
And I just wanted to, well, you highlighted, Maya, 2 pain points, which are the difficulty to access to data and also the difficulty to get it annotated.
Right.
And I wanted to get kind of a feeling on what is the biggest pain points among these two crucial elements, because I've been trying to better understand how to access more data. And to me, I've got the feeling that it is the most difficult step to access data rather than getting it annotated. But I'm interested in people's opinions.
Yeah. Yeah. So I will just address my part of things and let the actual deep learning developer answer that what they think is their biggest challenge. So the access to data is actually, we've seen more and more growing open databases of COVID-19 model, whether it's X-rays, more X-rays than chest. But what I'm hearing from the developers is that we see a lot of people using those data as a classification model because they know that this is COVID. The open databases are classifying those data sets into COVID positive, COVID negative. But however, when we look into more quantitative or segmentation models where we really want to have more information on the image, then we will look for annotations expertise, and this is what is missing. Is that correct, Sam and Rahul and Darshan? It's more like getting the segmented data, or
Yes, we need a medium of communication between the data and the engineer, deep learning engineer.
Yeah.
That's what I asked.
Yeah. So, I mean, we always would benefit from more data. So the number of data, the amount of data available is for sure a challenge. But I guess once we have that that data set, we need like the labeled data set or the ground truth data set to improve the model performance, or at least to like some kind of benchmark or validate them.
What I understand is that with the urgency of the coronavirus situation, we see more and more data being made available. However, it seems to be that the whole of the data is split in small data sets, and we do not have a lot of knowledge on how it was acquired and how basically we could normalize this data to make a larger batch of data we can use to build training sets.
Yeah, that is correct. I don't know if you other people on the call have other opinions.
Yeah, I can add a little bit of feedback
Yeah.
from a little experience I had trying to initially wrangle this when COVID was first released and everything. And I think we were contemplating, trying to make a very general annotations segmentation based project and get that in flight. And then it kind of, I guess maybe I made the realization, maybe I didn't communicate this publicly as well, but without having that clinical knowledge and the clinical backing of this, almost like I was thinking about the way Arterys does things, where we have product management really citing a very specific need for what model we want to develop and what problem we want to tackle, and then kind of working from there to develop a solution. So I think it was kind of an interesting challenge in this case that we had a lot of general people, there was Xray and CT, so two different modalities involved. And then there was a lot of different general ideas on how to tackle this problem. So I think trying to make a general annotations protocol, have a general data set, is something that I found challenging or found hard to execute on, just because historically it was to get very specific, to do one thing and to do that one thing well, to make sure that at the end of the day, we had a viable product. So maybe to me, it's just over complicating a little bit, but just the generalness that we need for the marketplace to, achieve all these different, the needs of all these different stakeholders and everything was kind of maybe made it a little bit more complex in my mind than it maybe needs to be.
So I don't know if we can summarize this as asking the correct clinical question, right? Like we need someone to be asking that question. As Albert said earlier, it's not all about triaging patients. Like we won't use imaging to say, oh, this patient is COVID positive, this patient is COVID negative. So we need probably more information about the quantification, where is the infection, how it's evolving. And this is where the clinical question and that transforms into annotations is needed. Did I address your question, no?
Yes.
Sure.
Thank you.
Awesome. So we still have 8 minutes. I don't know if anyone else has a quick question that won't require more than 8 minutes. Or else I'll give you those 8 minutes back. Okay.
I just have one question to Rohan and Rahul. Where did the data set come from again? It was UCSD, right? And you had a large data set. Did they open source it? And was it COVID or pneumonia?
So the data set was open source and it was on COVID-19. And yeah.
Oh, okay. And it was 300 images, right?
Roughly 350 images of COVID positive CT scans and about 400 of non-COVID CT scan images.
Great. Maya just posted the link.
I just posted the link to that data set.
Okay, great. Thank you.
Okay. Anything else?
Actually, I have a question for Rohan. How well is your model generalizing? Because the data set is quite small, I see.
Right. So to address that issue of the small data set, that's kind of the reason why we perform those affine transformations to kind of create basically more data out of our pre-existing data set. But in terms of generalization, as you mentioned, as you can see, like near the end, it kind of overgeneralizes, and that's why we kind of have that overfitting that you can see. But before that, I think the model was fairly optimal.
Okay.
You use callbacks, Rohan?
I'm sorry, what was that?
Do you use callbacks? Which is the framework you're using?
Oh yeah, so we used Keras callbacks, and then
Okay, you can write a Keras callbacks, like you can filter out the true positives and false, yeah, all those confusion metrics. I have written an example kind of thing in my GitHub repo where I like how many percentage of the true positive and the true negative are achieved, and then I short out the model with that.
what
So
is
maybe
your
you can.
GitHub repository?
I'll just post a link. Kindly wait.
That would be perfect.
Yeah, just a second.
Also, actually, I wanted to know about the test set, because what was your train test split?
We used a 75-25 split.
Okay. Okay, so you basically only had like 200 images for training, correct? Per class, that is.
I don't know the exact number, but because of the affine transformations, it basically multiplied our data quantity by 5. So I believe our train set was roughly 600 or so images, if I recall correctly.
Okay. Okay, I see.
So I will invite you actually all to actually continue this conversation on Slack. So we have a couple of channels where we can continue this. We have the COVID-19 channel, we have the model integration channel, and we have the ML general for more ML generic questions. So please feel free to reach out to each other there. I just want to thank everybody who connected to this webinar. It was great to actually see your faces and hear your experience and your questions. I hope you were able to find answers to your questions, and we will be meeting soon. So we will communicate later other dates for other webinars. And if you have any ideas or topics that you want to discuss, don't hesitate also to write it on Slack. Yep, and I will be sharing the recording as well for the rest that couldn't connect today. I wish you all a good weekend, happy Friday, and see you all soon. Thank you all.
Thank you.
Thank
Bye
you.
bye.
That's all.
Bye.
Bye-bye.
Thanks. Bye.